So let's continue. And we have until now talked about the cases that we have too little data. And one way to handle it is to augment your data. So you have some data, and by manipulation, you can actually expand it in different ways. And this can be done in different ways. So we have different transformations we can do. We can do shifting it in the image. We can zoom it in different sizes, rotate intensity changes, some normalization, scaling, possibly changing the colors, also shearing it. And on top of that, we can also add noise, and we can do more blurring to simulate different imaging conditions for the acquisition. And here's some example. We have, this is a retina scan image, so you can see the blood vessels in this picture, and this is what the ground truth should look like when it's segmented. And then you can do, here are some examples where we do some elastic, rotating, zooming, and then you can see also what the grid looks like. And these data were extracted from the DRIVE database, which has a lot of already annotated blood vessel images of this kind. And actually it was an extreme data recycling done by a master student of mine some years ago. And the purpose was actually to find root networks in soil. And roots and the blood vessels have kind of similar structures. So we actually recycled this data to boost the little data we had from the roots. And it worked out pretty well, actually. So what can we do? There are, of course, some limitations. So if you have CT images from patients, you cannot flip them around as much as you could with other things. For example, the organs have their places in the body, so you cannot flip them. So you cannot flip the liver upside down all of a sudden, and then it doesn't make sense anymore. So that kind of things. Also, the gray levels can also not be so much modified, because the Hounsfield units that you get in these images, they have a physical meaning, which means you can actually make tissue comparisons from these gray levels. So we cannot really change them too much, because that would change our interpretation later. And then it's also a question, how much can you distort the data and still recognize what it is? So you cannot stretch or shear something too much, because then it's not the shape that you would expect in a natural variation. So you need to make sure that your variations are within the limits of the natural bounds of what you're observing. For this purpose of generating these features, there is a tool in a package called Keras. And here is a lot of parameters. This is from just typing help on this data generator. And well, there's a lot of text now. And on the next slide, I have put it a bit more organized, maybe a little bit small, but anyway, here you can see what kind of information you can do. For example, we can have feature-wise centers, sample-wise centers, and then you can set true or false on those. You can see, you can do some kind of shift range. You can do rotations. So that would be plus minus 30 degrees, for example. And looking into the manual page of this function, you can set up your own augmentation within the bounds that are reasonable for your experiment. Here you can also see that flipping is not allowed. And when it's filling in, so all these operations require some kind of interpolation, and in this case the fill mode is set to nearest neighbor. So it's just taking the closest pixel for filling in. And looking at the MNIST images, you can see if that works now. So that's not good because I forgot to run this one. So let's do it again. So here we can see some augmentations, and if I go up a bit, no, I thought I could go up. Yeah, here he comes. So here you can see the two should look like this, but here it's shifted, it's a little bit rotated, shifted and not so rotated, maybe scaled, and so on. And you can see here what it does to the numbers. And already these variations help later to make your algorithm more robust, because if you train it just or tune it just for one case, then it's not so reliable. I mean, also as humans, we don't always write the numbers the same size and not always rotate to the same type, and that helps them to be more robust under such changes. Another large dataset is the CFAR10 dataset, where you have a lot of categories, and this is something we're going to also try with this augmentation. And again, let's do the example. Okay, good. And now running it, it's a bit of code, but mainly it's just to, and here you can see these images, they are quite small actually, and now I can't scroll, but in some cases it becomes a little bit strange, the result. So looking at this bird, I think, it's flipped upside down. This one is shifted beyond recognition actually, because the horse is moved around the corner, rolled over the edge. So that kind of augmentation doesn't really make sense. And that one is really extreme. I don't know what that is meant to be. So with this, when you inspect your augmentations, you can see if you are within the right bounds and if the augmentations are useful. So you have to do the augmentation with some care, and also check the quality to avoid the wrong kind of augmentation. Baseline. So the baseline is actually, now we come to an algorithm, a very simple one. It's used to compare the performance of the task, of a solution to the task, and it's a very simple, easily to implement method to do what we want. And it can also be seen as a worst case scenario, and this gives us the benchmark for later tests of our algorithms. If it's worse than this one, it's not worth using, so then we have to reject it. So one example could be that we have a model which is more than 99% accurate in predicting breast cancer. The algorithm is very simple. It just say no, because already that is because of the statistics. Apparently there are about 89 women in 100,000 that have breast cancer. So if we say no, we have a good predictor or not. It doesn't really make sense, but it's kind of a baseline. And for that, we can also set up a dummy classifier. In this case, it's called most frequent. So it's looking at the most frequent case. And we set it up like this. And then we get this dummy classifier as an object. And then we want to test it. And looking at the prediction. So we have this case. We have 3 healthy and 1 with cancer. And most frequent actually gives us the result that all are healthy, because healthy is the most frequent case. So that can be used as some kind of some kind of baseline. It's not so smart, but it can maybe be a starting point for doing the analysis. If you're worse than that, then you're probably just guessing. So let's look at the numbers. So here we have just our data, our numbers, 0 to 9, and we want to see if our classifier does well on that. So let's again try the dummy classifier, most frequent, and we got it. We try to predict the images from the MNIST, and here we got. Now we get the result 1. All images are 1. And the reason for that is that 1 was the most frequently appearing image. And looking at that, again, we can see here the output. We get that all are predicted as 1. And looking further on, we can see that looking at the histogram of every number, we see that, yeah, the 1 is actually the most frequent, so that is the winner in this dummy classifier. A little bit smarter one is using the nearest neighbor, and this is an algorithm that I'm going to talk about more in a couple of weeks. But in principle is you have a data point, and when you get that you compare 2 points you already have, and the one that is closest to the one I have, closest to the measure one, tells you the class. So for example, if we have 1 point around here, the closest is actually this point, so we get the blue. If we are just on the other side of the border, one of these are the closest ones, and that will be the one telling which class you have. So that would be the pink class. And the simple case is you only look at one neighbor. The more complicated case is you look at a number of neighbors. So then we could talk about the k nearest neighbor. So that, that one has 9 neighbors that it compares to, and you can see that the boundary is getting more homogeneous in comparison to this one, which is quite uncertain. So if you want to improve the accuracy of your nearest neighbor, then you can increase the number of comparisons. So let's load the data again, and then we get the numbers. And we train it with the k nearest neighbor. And in this case, we just use a single neighbor. And we train it, and then we got our training box here. And then we want to predict, again, with our images. And that should run, yeah. And then we get the sequence. And if we compare this sequence with the data that we had, we can see, wow, all have the same prediction. And do you have an idea what is the reason why we get the exact 100% prediction here? So there is a little mistake we did here. You want to say something? Yeah. Yeah. So the thing is, we actually did the test on the exactly same data that we trained with. So of course, the 1 fits on the 1, the 5 fits on the 5, and so on. So that's why we got it. But if we now would take a different data set that we compare with in the test, then we can see that, oh, it's not that good. So this should be a 2, but it predicted 3. This should be a 4, but predicted 1. This one actually got it right. But, and these, now we have some good ones, but then it's not so good anymore when it's comparing to a different data set. And this is actually what we want to see. So when you do these comparisons, it's always important to have one data set for the training and one data set for the validation. Otherwise, you do the wrong thing. Another thing is that we want to know how good are we actually when we do our comparisons. And for that, there is a tool called Confusion Matrix, which is organized like this. We have two categories here, actual true, actual false. And then we can see how good the algorithm did. So this is what the algorithm predicted, if it's predicted true and predicted false. And the part we want to see is actually this diagonal should be as big as possible, and here we should have as little as possible, because those are the misclassifications. I will come to the confusion matrix in later lectures too, and in more detail, and see what we can get out of it. And if we look at the confusion matrix for this MNIST example, we can see that the diagonal has pretty bright results, but there are some cases, for example, the 2 is sometimes confused with a 1, and here is a real bad example where the 4 is confused, actually more confused with being a 9. And there are some other examples, I think. But yeah, so you can see that with this tool, we can see where it does the misclassifications, and maybe also where we have to put our efforts into getting better. Here we got apparently an accuracy of 56.9%. And this brings us to the end of generating the data sets, and now I'm going to switch to a more technical part, which is Dataframes. That's a way how you can organize and store your data while you're working with it. So we have our workflow, which contains some image analysis that extract features for our analysis, and then we want to present it in some way, if it's a table or if it's a plot of some kind. But the question is how we can store our data in this process. And we have our features, and now to store it for doing the analysis, we want to apply different operations maybe. We want to count how many do this or that, or we want to have some statistics, averages, variances, maybe do selections, filter out different features of different kinds, possibly do some transformations and visualization, that would be plotting the results. And when you work with Python, you have different options. You could store it in arrays, one array per feature type. You can also use data structures or dictionaries, which is a more structured way. Actually, the dictionaries and data structures probably contain arrays. But setting up this kind of data structure and all the operations related to it can be kind of time-consuming. It's also less flexible, because once you have done your data structure, it's quite rigid and it's hard to export into or expand into other use cases. And of course, when you start code yourself, you come into an evil loop of making errors. So better rely on something else. And for that, we have the data frames. The ones I'm going to talk about here are called pandas. And the idea is that you have a data container which is organized more or less like a spreadsheet. So you have columns and rows. And then you take any data actually in the cells. It could be strings, could be numbers, could be arrays, could be images even though I don't really recommend it. But you could have actually anything in these cells. And what you can do is you can filter, making selections within this data frame. You can also sort the information according to one or two rows, perform the arithmetics, compute statistics, and also very important, you can actually also do file handling with it, so you can read in and store the information, either in the form of a database, so there are even database backends to these data frames, or you can also, for example, put it in an Excel sheet, or you can put it in a comma-separated text file, whatever you want to do. The Panda documentation, getting started, is a very good source when you start working with it. In particular, getting started helps you a lot when you want to work with it. And I'm going to, during these lectures, use the data frames, so you will see it here and there that I'm working with it. So, there are different ways to create data frame, and the easiest way is actually through a dictionary, but you can also take it from a data file, which is formatted in the expected way. And you can also take NumPy arrays. And to get these data frames, you just have to import pandas. Traditionally, it's abbreviated with PD. And now let's read some data. Yes, from a comma-separated value file. So it's a text file with commas between the numbers. I think the first row is even labels. So if we look at this, you get here, you read the data. You can see you have a lot of categories in the columns. And this sample 5 means it takes 5 random rows from this data. And you can also see that they are random, they are not even ordered. So the first number here tells which row number it is, and they are not even ordered here. And saving to a CSV works the same thing. In this case, so we had read CSV here, and now to CSV. So that would just save this data table. And another way is to create it from dictionaries. So in this case, I have a little piece of Python code. What I'm doing is I'm starting with a list, an empty list. Then we do a loop over 10 values and create small dictionaries. One is position, and then we get the value of the I, and the sinus value comes in the second column. So when we have done this, we have a list of mini dictionaries, so position, sign, and so on, and 10 of those. When we now put it in a data frame, we take this list of dictionaries and say we want to create a data frame, and looking at the first 5, so head means that it takes the first lines, and number tells how many lines you want to do. So we could also do head 2, and then you get just the first 2. The opposite is tail, so then you get the last element. And then you can, of course, also do sample as I did in the previous example. So an alternative is to instead make a dictionary where you have 2 labels, and the content on each item is an array. And then we create first the X, which is just 100 values between 0 and 2 pi. And then we create another array, which is the sign of X. And we create a dictionary here with the position and the sign value. And that works the same way. In this case, you can see again, we have the position in one column and the sign in the other column. So this is just how you can create it. Now comes the fun part, is that when you start do calculations on it, say you want to add a column, then it's quite easy because you just, if the column doesn't exist, it's created. So here I create the cosine, and then I do the NumPy operation, so cosinus of the data frame position. So then it takes all the values from the position column and computes the cosine. Then we want the sum, which is the value from the two columns, sine and cosine. And then we want to check if it's positive, and then we do a Boolean column where the sign is above 0. And then we look at what that creates. And here we got, from the previous one, we have now added 3 columns. And then you can see here that we got the cosine nicely, we have the sum of them, and we can tell if the sign is positive or not. So that is the way how you can expand and build up your table. And then you can do, with this, you can do some filtering. So for example, you want only to see the rows where the sign is positive. And there are different ways. One way is you create a new data frame which contains, here you have the criteria. So now looking at the column sign, if it's greater than 0, and then you get the 2 here, df2. The other way is you look at the positive column, which we already have done this testing, so we did the calculation already, so you don't have to recalculate. And it's also increasing the readability if you do it this way. And then we can look at the result. And now we can see that the output in column in data frame 2 is only the positive values. Yeah, so here you can create more or less complicated filtering. You can also use the Boolean operations and an OR to select even more detailed. Then sometimes you come to the conclusion that, oh, I had the wrong names of my table columns. For example, if you import it from an Excel file and the one who made the table from the beginning didn't have, in your opinion, the smartest names, or they are too long to be practical, then you can rename them. So here in this example, I create first a data frame with A and B, and then I rename them to A gets hay and B gets hop. And then you can see afterwards what that looks like. So here we have the A and B, and afterwards, same table, but now the table column labels have changed name. Little detail, useful or not useful, depends on your application and how you work. What is very nice is that you can compute a lot of statistics from your data frame. So you can do df mean, which means it calculates the average value of each column. So here you get a summary of all averages. Even the Boolean, it's an average. So we see there is 60% chance that it is above 0. Another way is also to use the df describe, and that gives you even not only the mean, but also all the statistical information. So it tells how many you have, the average, the standard deviation, the minimum value, the different quantiles, and the maximum value. And that is extracted without adding too much code, so you get all this information straight away. And then you can also do the statistics with filtered data. So you can do a filtering as we did before, seeing that if sum is above 0, then we should compute the standard deviation of the sign column. Then you can do that kind of calculation. So you can do really more and more complicated expressions here. So this first part here creates essentially a new data frame, and then from that data frame you extract a specific column that you calculate on. Even more complicated is that you can bunch things together. So now you want to group your analysis in here by the categories or the results in, oh, where am I? Here I am. By the group positive, and then we can say we want to do some operation on that and see what the result is. And then you can see that we grouped it by the results in positive, so we have the categories true and false, and then you can see what the position average is, the sign average, the cosine average, and the sum average in each of these two categories. And that can be helpful when you start doing analysis on your data and want to do some extractions, for example, on different shapes, or if it belongs to different categories, like it's round or squared or whatever. But that may be a bit too much, too cluttered, so we can do a lot more complicating things, where we first group it, and then we want just to compute something around a specific value. So in this case, I want to do the statistics only about the sign, and then I want to compute the average and the variance from that. And here we have information about the sign column. Another nice feature of the data frames is that you can do plotting, and here I show that you can actually just plot all the columns. Maybe not always make sense to plot all at the same time, but I'll show you soon how to plot specific columns and combine also specific columns. But in this case, I'm just dumping everything. And another way is to select. So in this example, actually I can do the plotting already, and then I can explain. So in the first example, we extracted only the sign column and plotted in axis 0. So with this subplots command, you can have several sub-panels that you plot in. And this variable is actually an array. So I'm telling in axis 0, that is the first panel. Then we want to plot the sine curve. In the next one, we want to plot the sine column as x and the cosine column as a y. And that's why we get a circle. And that is put in the middle panel. And then we set some title on it. And here I do some filtering and plot x and y from that. No, x as the position and cosine for that. And that under the criterion that the sign is above 0. And then you get that kind of plot. So you can do a lot of creative plotting here. You can actually even do more. You can do bar plots, and you can do scatter plots like this. Again, in this case, I took all data. In the scatter plot, you can see the points around the circle, but you don't draw the lines between them. So this is quite useful when you start getting statistics and have different categories. Then you can get scatter plots, so you can see actually where you have the distribution of different features inside. But I'm going to show that in also a few weeks, examples on how that is done. And well, we can actually do a lot of set operations combining different data frames. This is more an advanced topic, but it's also covered in the Pandas documentation. So here we have different data frames that we want to put together, and there is concatenate, and that is resulting in a bit strange result because the indexing here is just repeated, because this one has indexes 0 to 1, and this one 0 to 3, and this one 2, and that's why you get the indices like this. So instead, you need to create, let's see, oops, yeah, there he comes. Create an index vector that tells how to sort them, then you get the index correct. There are also other ways you can redo this, but I don't know it by heart right now. Another one is merging, and then you can have adding columns, and here we have A to D and X to Z, and here they are combined on the same rows here. So finally, you can also create new columns for a new data frame from selected columns. So previously, say we did all our calculations and realized the cosine is not needed anyway, and also not the positive. Then we can create from a given data frame. We can select that I want to have column A, C, and D, and then we can create a data frame from that, and then you only get those columns in the new data frame. So it can be good to cleaning up when you want to store your table afterwards, after you have done your operations. So when are data frames actually useful? I would say in the beginning, the data size is very large, and if you have a lot of data, Pandas is limited to what you can fit in the local memory. There are other data frames that can handle the large data. So for example, the Dask Dataframes, they can handle it. But in principle, when you have large data size, so the raw images, it doesn't really make sense to bring them into the data frame. Segmented images, a little bit less data, but then when you come to the feature data and even statistics or modeling, then it gets more and more relevant to put them in the data frame. So it's in principle the data size, when it shrinks, then it's more relevant for the data frames, and also the level of abstraction you produce is also giving you a hint on if it's useful to put it in the data frame or not. Brings me to the end. So we looked at different data sets produced by other people, maybe by you in the future, what you need to do if you have too little data, and also a first glimpse on baseline algorithms to have something at least to compare your analysis, how you do it. And as one metric or one way to measure the performance, we looked at the performance confusion matrix, which tells you how well it actually reaches the result that you expect. Finally, I added also the data frames, which is a nice tool how to work with the data, and here creating, selecting, combining, and also some plotting. And next week I'm going into a more, say, classic image processing task, which is talking about noise in the data and filters to reduce noise, filters to enhance information, to extract information from the images. And yeah, that was the end of today.